still don't know what is a dark matter. Yeah.
Well, we are trying to determine the mass. I think we are making a progress today. They should be fermions and of 50 keV.
Oh, 50 keV.
Yes.
So 10 years ago, I started chair lectures in honor of Professor C.C. Lin, who graduated from Tsinghua University in 1930s. And he was a great applied science, applied mathematics to astronomy and many other important subjects and fluid dynamics. So he has proposed a great theory about galaxy, a spiral galaxy. And so I'm very glad that this year we finally invite a great expert on this theory, Professor Ruffini from University of Rome, and he's going to explain some new phenomena and new physics. And we are very glad that it fits well. Not only him, he will be has a whole group who are going to give several lectures. Okay, thank you.
Thank you, Professor Yao. Well, it was a great occasion for me to prepare this lecture, which is the first of a series of lectures which we will have here during next week with our group, with Professor Ueda first, with Yu Wang, then with Shesheng Sui, and then with Rahim Moradi. This is a beautiful picture from the Fermi satellite of our universe. And here you see mainly the contribution of our galaxy, and here there is the Crab Nebula and this Geminga. These observations, there are 3 slides. One, this is the universe in gamma rays and X-rays. But I am going to attempt today to introduce you, visiting first the work of C.C. Lin, to this author description of our galaxy, the Milky Way, and in particular, the work that C.C. Lin did for understanding the structure of our own galaxy and the spiral arms of the galaxy. And this will bring us automatically, and I enjoyed very much to prepare this lecture, to a third vision, a third topic. This is in the optical. And there is a third vision of our universe and of our own galaxy, which is dark matter. Black. We don't know. We cannot see dark matter. We cannot see dark matter. We don't know yet the component. In this case, there are baryons. Here there are black holes, which will be lectured in the next week, neutron star. Here, we don't know the components. We don't know even if they are fermions or bosons. And how can we know something of this? We don't know yet. And I will show you that maybe we are progressing today in learning more about the fermion component. But what we know that 90% of the mass of the galaxy and probably of the universe is in dark matter. I mean, I want to show you today why we are so certain. We don't know anything. We cannot see. But we know that 90% of the matter must be dark matter. This is the key point. Okay, let's start with the lecture on Sicilin. Everything starts in last century by, of course, the classical work of Einstein and the work of Planck. But if you go to the next step, the work of Werner Heisenberg has been absolutely fundamental. And this was his thesis. And maybe people know that the thesis was not accepted with furor of enthusiasm. The man who gave the thesis topic was Sommerfeld. The topic was about turbulence in a canal, very similar to the lake you have in front, a little bit more turbulent. The thesis was difficult, and Heisenberg did not succeed in completing the work. And he failed the exam also later because he did not pass. There was an experimental part that he did not pass, and therefore he had to leave Göttingen and Munich to go to learn how to do experiment from Niels Bohr in Copenhagen. And paradoxically, in working with Niels Bohr, he introduced the indeterminacy principle exactly on something that he missed in the thesis examination. And it was corrected by Niels Bohr. But when we read this thesis, the other group reports which achieved great success quite recently was von Karman. Here is a man which started to lead us to Sicilin bit by bit, but I will go by step. I like this picture very much because I can be informal maybe. The German, he escaped from Nazi Germany, and they told him, please come back because we will not do anything to you. You are too important for us and so forth. Von Karman, who went to the state, sent back this picture and said to Göring, would you take me back with this nose? And of course he did not accept. But anyway, the key point of von Karman is that he had a fantastic collaborator from China. And it was not Chao Lin, was another one, which I had always a very, very, very deep respect for him. And I wonder if I met him once, many years ago, in the hall in Tiananmen. But Sicilin became a student after, of course, the fantastic work that he did in Tsinghua University, guided by Cho Pei-wan, because Cho Pei-wan told him, go to not to aeronomy, to space, to the fluidodynamics. And he followed this advice, and he ended up with von Karman. And von Karman, of course, gave him the thesis to improve Heisenberg's work. But there was at this time in the US in the University of Caltech, not only von Karman, who is here in the first row, the seventh, but also Shui Shen Tian, here, this man, who later on became the father of the two bombs in China, after being the founder of JPL and all that, and he was the founder of the Long March rocket, which has given the greatest progress and still has greatest progress in China. From this triptych, von Karman, Shui Shen Tian and Chao Chang Lin start the story of re-examining Heisenberg's work. I followed with enormous pleasure the preparation of this lecture, and I enjoyed very much reading an article published by one of the closer collaborators of C.C. Lin, Frank Shu, who published the first paper on galactic structure. But in that article, and I think it's important to understand this point very much before going to the galactic structure, there was an essential dispute between C.C. Lin and Pekeris. C.C. Lin was following the path of Heisenberg, proving that he was correct. Pekeris was against both the work of C.C. Lin and the work of Heisenberg. And finally, in this situation, Wu jumped in, brought in by von Karman, was nobody else than Johnny von Neumann. And Johnny von Neumann, now you remember at Princeton, where we were together in 70, they were the housing of the professor, but in the corner between the housing and the building, there is a small house, small red bricks, and this is still called the computer room. It's nothing inside. If you walk, you see it's empty. But in that room, von Neumann built the first computer of IBM. And people in Princeton neglect this. And there is where IBM was started. And von Neumann, you realize, von Neumann here is with Bob Oppenheimer. Please, every time you go to Princeton, go to the institute and pay homage not to the building and so forth, to the small house. It's not more than 5 by 10 meters in bricks. Very simple. There is von Neumann put the first computer. And he used the computer to prove that C.C. Lin was correct. Now, this is the first part of the story. C.C. Lin had a tremendous background, one of the top in the world, because he managed to understand better Heisenberg and to explain why Heisenberg was correct and to propagate this. Therefore, he was a person of extreme and strong. While he was in Princeton, as you remember, in front of the Princeton building, there was Oppenheimer House. Then you could continue a little bit. There was Regge House when we were there. In the Regge House was living Professor Strömgren and the one on the left. And Professor Strömgren was very, very interested in galactic structures. And with Strömgren visiting continuously was Jan Oort, the man who had discovered the flat distribution, that the distribution of the galaxy was due to rotation. This man was the one to discover this, Jan Oort. And it was an incredible opportunity for C.C. Lin, visiting Princeton, to do some other work on low temperature superconductivity with Fairbank and Hsien Yang, visiting, that he followed in the tea time and so forth, meeting with Strömgren and he was the man. These people are not the way to fluidodynamics and so forth. This was impossible for them. They were just mapping, but not being able to do the physics of this. And this was the starting point of the study. But let me introduce something which was missed for some reason by C.C. Lin. The first person to look at galactic structure was Enrico Fermi with Chandrasekhar. And Enrico Fermi and Chandrasekhar did a beautiful paper and understood that the galactic structure were due to also to the presence of magnetic field. And from the polarization of light in the galaxy, Fermi, with his usual mastery of physics, determined for the first time that the estimate of the magnetic field in the galaxy must be of the order of 10 minus 6 Gauss. It's a beautiful paper. Please, if you enjoy physics, read this paper. It's marvelous. Simple, 3 pages. And also the diplomacy of Fermi, expressing criticism and praising other people. But what was the problem? The problem is that if you take a galaxy rotating as a rigid body, the boundary rotates too fast. If you follow an approximation that all the stars follow circle, like Babbage did, the arms winds up. Therefore, you cannot have rigid body. You cannot have circular trajectory. What C.C. Lin understood, and this work was the fantastic work that he did, I have there the original with Frank Shu. This idea that the spiral structure of the galaxy comes by elliptical motion with precess, with some regularity, and he wrote the equation for this. And therefore, you have the density wave approach. For no wave, you have just randomicity. For bar wave, which are locked in, you have there. But for spiral wave, you can form this collective motion which represent the spiral of the galaxy. And I could continue, but it's impossible to continue on this. But I like only to show one of the pictures which was selected as a proof of the validity of this theory by Frank Shu in this beautiful article that he wrote. Very short but densely, beautifully written. And why I'm so happy to show this? Only one paper, recent. Jerry Ostraker is a good friend of ours. You remember him, he came at the Grossman meeting to give the same. Now, Jerry has a daughter who is also an astrophysicist, and Eve Ostraker. And the thing I like most about the work is a work by Eve Ostraker, the daughter of Jerry Ostraker, about the global modeling of formation of galaxies. And the reason why I like very much, not only because Jerry is a good friend and this paper is very impressive, but the conclusion of the paper, our model also suggests that magnetic fields are important in preserving the grand homogeneous field structure when gas in the Orm fragments via self-gravity into this system. Therefore, this in a certain sense is, but from now on you can go only with super computer, and you cannot make any progress just simply out of first principle. But in this paper, the work of Fermi is vindicated and shown that it's very important. And here is the beautiful picture of the spiral galaxy observed in reality, observed by the NASA, and the simulation done by Ostraker and collaborators, mapping practically the data with the density wave profile of Sicilin. So much for this. But I would like, before going to the new science, or the dark matter, celebrate another person which I just mentioned in the beginning, Chope-1. And here is Chope-1 at ICTP in Trieste at the second Marcel Grossman meeting. And here is Dirac, Paul-André Marie Dirac. And I like very much this picture. And also to say something that this Marcel Grossman meeting number 2 was essential in convincing Chope-1 to organize MG3 in Shanghai. It was, like I was mentioned to you last night, the most difficult diplomatic work I had to go in my life, because everything was prepared, but the point was not have Israeli coming into China. And I said, it's impossible. I mean, the meeting cannot go on without Israel. I mean, it's Einstein theory. How can you have Einstein theory and not to Israeli? This was the most difficult bargain of my life, because I came to Beijing alone, imagine. Not in as usual, I go alone. And in front of me, I had 13 people sitting, and we were in a beautiful villa near Tiananmen, secluded. And every day, from morning to evening, we had this confrontation. Why this man does not come with his Canadian passport? Well, I mean, this is up to him. But my friend in Israel was the Minister of Science. And the Minister of Science was not a trivial person. And he recommended, Remo, you must obtain one Israeli, one. Do whatever you want, but one must go to China. Do whatever you want. And I bargained for 1 week. It was terrible. I never gave up. Finally, on Friday morning, we decided to pack, to go to the airport, forget about, okay, we canceled the meeting. We were ready for breakfast to cancel the meeting, and then a phone call came. He said, there is a message from the foreign minister. I said, well, it's too late, we cancel. He said, no, there is a message, please. Okay, let's go and see. And the message started, we will never put the finger over a passport of Israel. Okay, I stood up and said, okay, thank you, bye-bye. And they said, no, sit down. And then they said, however, but I start to understand what was the problem. The problem is that when we came to China, there was all over the walls a sentence. Friends from all over the world are welcome. And this goes back to the emperor. Friends from all over the world are welcome. And then I explained to Chope-Wan, this is the problem. We have to change, the courage to change. And right, scientists from all over the world are welcome. It has nothing to do with friendship. It is a duty towards science. And the last sentence of Chope-Wan, finally, what it means, this finally. I would like to take this moment to wish you complete success in your endeavor here. I believe that we are all taking a significant step toward the creation of a truly international community of scholars. And this was epochal because the key point was to invent a document. And the foreign minister said, any document agreed between Professor Ruffini and the ambassador in Rome. I did not know what it meant. I had an international driver license, and they showed, this will be okay? And he said, we don't understand the question. Well, I said, is this okay? You have to judge, not us. Therefore, I understood I had open possibility. I had no limit. Therefore, I decided to create a new passport with the picture of two distinguished scientists. One was Zvi Piran, and another one older, but the conditions were to be young. Of course, I said young doesn't mean anything in China because everybody is young up to 95, therefore it's no problem. Then or over, because the next step was not to be politician. Therefore, the minister was out. But he told me one is enough. Therefore, I was safe. And then they said two. Oh, I said, we made it. And we made it, and the meeting went on. But I think later on, the community in China was enormously grateful to the Grossman meeting, because from then on, there were no more problems. And of course, Yuval Ne'eman, who was the Minister of Science, you know that Yuval lost the Nobel Prize. You know the story. He was student of Salam. They had a meeting in Tri. And then Gelman went out of the meeting. He published, got the Nobel Prize. And the author was Ne'eman. Therefore, Ne'eman was not a trivial person. And soon after, the year after, he was received in China. And now the relation between China and Israel are blooming. Therefore, let's go back now to science. Where was the big new revolution? Okay, this is a nice picture of Chao Lin and Chope-Wan. The physics of dark matter start without doubts, from the most gentle transition you can have in physics. A proton and an electron having the flip of the electron from a spin up to a spin down, and the transition emitting a 21 centimeter line. This is a gentle transition. And Lin had proven that the galaxy had a spiral structure, and these are two beautiful pictures. But what was discovered by Sanchisi, who was working in Netherlands, is that if you look at the same galaxy in the radio, there is emission in lobes in the radio with the velocity going on one side positive and on the other side negative. And this is gentle. It's emission from non-ionized hydrogen, cold, around a galactic structure. And here you see the map for different velocity, plus and minus. And if you consider the difference between the center velocity, 670 kilometers, 820 minus 670 gives you the velocity of coming of that side. And 520 measured minus 670 gives the velocity outgoing. And as you go at a different distance, you see that the rotation curve of the galaxy, instead of diminishing, is practically constant. This is the great discovery made by Sanchisi. In other words, the matter, the hydrogen around the galaxy rotates, blue shifted for the particle coming toward us, red shifted for the one going away from us, and the velocity of rotation is practically flat. Therefore, this is the fantastic result, simple, clean, not nuclear physics, not strong field, 200 kilometers per second, constant. The data are very subtle and very, very clean. And if you find the rotation curve of the galaxy from the visible mass, is this one. As soon as the visible mass decreases, the velocity should go down as 1 over square root of r. And instead, from observation, the 21 centimeter line, the velocity curve is up. And then there is a result which is not to be discussed any longer. The fact that this flat rotation curve, the difference between here and this, it gives that 90% of the galaxy mass is there. It's not visible. Has nothing to do with stars. It's not visible. It's dramatic. Is clear at this point? I mean, if you just look at the rotation curve, 90% of the mass is there. It's not visible. And then this started, this very, very strong research. Much of this research was based by my first work of thesis in Rome, published in Princeton later, after 2 years, after going to Germany, working with Pasquale Jordan, and then working for 2 years in Princeton with Wheeler. I corrected this article with the system of self-gravitating particle in General Relativity. both for bosons and for fermions. And this is the paper which has been enormously quoted, which we have used for fermions to try to identify the nature of the particle forming the dark matter. The fermions work in the dark matter. I don't want to go through the equation, but we can study a massive fermions we cut off in space, and I don't go through all the mathematics, but we have a density profile being computed, and the velocity of rotation, and then we have defined as well. Here are the results. We can explain with the fermions. The baryonic matter is this one, with the fermions of 48 keV. This is the flat rotation curve being explained up to 50 kiloparsec. Therefore, the flat rotation curve can be expressed with fermions of the order of 50 keV. Therefore, this was known for quite some time. We published this, I think, 6 or 7 years ago. Quando l'abbiamo pubblicato? 6 or 7 years ago, no? The first RR. Yes, anyway, maybe 7 years ago. But we could explain the flat rotation curve. But there has been something which came out of first principle. Therefore, we can explain the rotation curve, but if you go toward the center of the galaxy, there is something there, and the question is, what is at the center of the galaxy? At the galactic center? A black hole or something else? In the galactic center. And this has been by far the work which has been more exciting, and the latest data have been published practically the day before yesterday. To zoom in the galactic center, there is, here is the galactic center, Sagittarius A, and if you go more and more in, this is the object we are discussing today and working today with Orge and with Wang Yu and with Shesheng, is this object over here. Namely, there is an object at the center. We know from this trajectory, let me repeat again, no? How can we go on again once more? Here. There is some material which reach 6,000 Schwarzschild radii away. What is there at the center? There is another work which has been done, also extremely exciting. There is a star, a set of stars, which goes around, goes away, and then zoom back in, the second time around, and here is the object, the center of the galaxy, which is invisible. these data are practically been collected with the largest telescope in the world, with the VLT, and with the largest technological effort from Europe. Also, it has been proven that as this S2 star you have seen, when it zoomed through, is gravitationally redshifted by Einstein equation. You see that. And therefore, what is there? Is there a black hole or not? To me, the striking aspect is that the more you look in this system, either passing or with nothing happens there. It's not like a big black hole we are using gamma ray burst. It's not active. And when we make our own theory about, and this is the one we are developing in this house, is that if we explain the rotation curve flat at big distance, as you go in with the star S2, you can as well form a dark matter core of dark matter, which you cannot distinguish from the black hole experimentally. And this is the key point of our research today, which we everything will be okay, we will publish soon. We are computing with Orge and with Shesheng and with Wang Yu. These are the data of a paper which is, which one is 22 of November 2018, just appeared. And there is a discrepancy between the Keplerian motion, this one, and the real data. You see, the Keplerian motion, the black, does not follow the data. And in our opinion, which we are working, and we will once more dedicate this result to the Yao Institute, is that we think that the core of the galaxy of dark matter is different from a black hole, it's more extended. And as the S2 star goes in, it's affected by the mass external to the black hole, the distribution to be not point-like, and this is what creates this difference. We will know within a few days, and we will let you know. Therefore, is to bring you up to the latest result. How is dark matter affecting the work of Lin? Well, quite a lot, because on the right you have the distribution of the spiral in a universe without dark matter, and on the left you have the spiral with dark matter, and therefore it's very, very different. Therefore, the dark matter, 90% of the universe. Now, what we are trying to determine is the mass of the fermion. If it's 50 keV or 52 or 53 keV. Therefore, it's fantastic that we don't see anything. We cannot see anything from dark matter. We choose the fermions to be correct, and we determine the mass, and we have the way now from the data to determine, and we know that 90% of the matter is not due to electron or proton or baryons, but is very likely a fermion or spin 1/2, not charged, and of mass around 50 keV. Why the universe is built like that is a big mystery. But our work in these days today, this morning, and you were there when we find out the result yesterday, and we think that there is the possibility to determine the mass, although it's not seen. But the strength is fantastic because it's almost Keplerian orbit. And there is no way to avoid that 90% of the matter be in dark matter. Therefore, this concludes my presentation on CC-Lin. In the next days, you will hear about a different topic about the Crab Nebula, the neutron star, our work which we introduced, the black hole with Wheeler, the mass formula, this beautiful picture of myself, and just in time, few months before Stephen Hawking passed away, we celebrate the mass formula with him in his house in Cambridge. Roy Kerr is in the back, and we had a splendid dinner at home. And then, of course, out of the mass formula, we had the great joy to deliver the Marcel Grossman Award to Professor Xin-Tung Yao. And here are the ceremony where I'm reading with the same tie of today the award. Here is Roy Kerr giving the award, and here has been the spectacular ceremony at the University of Rome. And of course, we are very interested in the work of Professor Yao for the work done with Richard Schoen about the positivity of energy. And the key point is the reducible mass, which we introduce and which was then discovered from the black hole, from the UHURU satellite, and then the Cygnus X1, the discovery of the first black hole, then CNX3, and then my award, Cressy Morrison, for discovering Cygnus X1, and then you have to wait. If you want, it's like wine becomes better with the year. I got the award first from 1973 from the New York Academy, but if you wait a little bit, the price will be higher. And therefore, the prize went to Ricardo. Of course, he acknowledged my work very much, but he was the discoverer of Cygnus X1. After this, let me tell you the great discovery of the gamma ray burst, which will dedicate the entire next lectures. But we dedicate this because there was, after the discovery, a fantastic person in Princeton who was Bohdan Pashinsky. And Bohdan, before dying, did two fundamental papers. And these two fundamental papers, one was with Mao Shude, which we are going to see him, I think, in the next day. And the other one has been Lixin Li, who, again with Zoltan Pashinsky. These two papers were absolutely 100% correct. 100%. But they were not supported with the data. We read all this paper, but we were not forced to say they are right. And we have developed with Wang Yu, with Shen, with Orge, the work on gamma ray burst. Now, after many years from these articles, 98, after almost 20 years, we can prove that they are absolutely correct. and give all the details of seeing the formation of the black holes, seeing the formation of neutron star practically once a day. And this story will be narrated by Orge tomorrow, followed by Orge did this fantastic work about the supernova exploding in presence of a binary neutron star. These images, why they are so important? They are very important because a gamma ray burst we see today with the satellite exploded 10 billion years ago. Therefore, it's not possible to have a picture. You see only the photon arriving. But from the equation of Einstein and from the computer and the tracing of the orbits, we can rebuild precisely the object when it exploded and how. We have used the largest computer in the world, which are the one in Los Alamos, to make, with Laura Becerra, a student of Orge, to do this fantastic picture. And then you will hear directly from Wang Yu our discovery of the supernova, which was discovered here the 15th, we predicted the 15th of the 15th of August this year. And here we are with Professor Xing-Tung Yao the day we understood this system. Now you can say, you can see on the blackboard, okay, what we draw by hand. You see that spike? That spike, we draw. We understood immediately what it was. And here it is now, analyzed, submitted to APJ letter, and the referee said, how did you manage? You have submitted the first paper on this source before anybody else. Of course, because we predicted. We predicted, and we have done all the theory. And what is fantastic is that the supernova which comes out, we discover, is a standard one. From now on, we will keep going. We will keep going to study even larger black holes of 10 million light years in mass, not just in gamma ray burst of the order of 10 or 20, 50 solar masses. We will move to understand, because we have understanding new in the last days, and we convene here because we are making the last step to understand the emission process of this high energy emission coming from the center of black holes. And this work, of course, has been made possible by many collaborators. We thank Professor Xing-Tung Yao for participating to the ICRANet activities, for inviting us to his institute, where we have been and we are being inspired. And we just close with the mind that allow us to do all this.
Well, thank you very much for a beautiful talk. Are there any questions? Yeah.
Thank you very much. Hello, Professor. Thank you very much for your really good review talk. I have a quick question about this 50 keV dark matter you predict. How about, can you explain large-scale structure with this very, very warm dark matter candidates rather than on the small scales?
We are, my opinion, we are starting a new science. It's the science of the INO. We call them INO, particle around KV. INOS. It's a new science. When particle physics started, you had the electrons, you had the protons, the neutron, and bit by bit, all the population of particle and resonance was developed. Now we need to have the key to understand the INOS which compose the center of our galaxy. Because there is where we have this fantastic data. We just arrived a few days ago, the 22nd of here. The 22nd, you have this fantastic data. You have the star going around the galactic center, turning around. These are exquisite data. Therefore, there we have to concentrate and find out the mass, if it's 48, 49, 51, 53. But I would like to ask Jorge to say his opinion. Focus there. And then that mass will be the INOS composing the galactic structure. But as you point out correctly, on large scale, you cannot do with 50 kV. Therefore, on large scale, we have to augment the statistics, more data on large scale. And our feeling is that there we have an outer INO, not the same one, but smaller yet mass, maybe 2 or 3 kV, smaller, for the large scale structure. And they don't, this does, in other words, the INO physics is just starting. And we need to put all the good data like this one to establish their mass. But what is clear, as you point out and clearly you realize, is that the large mass distribution, both in the galaxy and outside the galaxy, is a factor 1 to 10. 90% is dark matter. Therefore, this is a real frontier.
So does the dark matter have angular momentum or anything, or all those standard?
This is the exact part of the exact problem, that if you look at a black hole, as such, like the last one I showed, the black hole as such has a lot of angular momentum and has jet. But this object is cold, has no jet. Even when a star goes by, does not do anything, does not accrete, nothing. Therefore, this object has no angular momentum and cannot be a black hole because it's too soft. And this is the computation we are doing right now. In our opinion, it's just what is the key point? No, maybe I missed to tell you the key point. The key point is when we study the flat rotation curve far away, at the order of 10 kiloparsec away, flat, in the theory of our fermions, 1/2 and so forth of 45 kV, it comes automatic that there must be a core at the center. This is given by the equation. You cannot have the flat rotation curve at a large distance in the theory from the self-gravitating fermions, which I introduced in my thesis. You need to have a core. And that core is a necessity of the equation. And that core is precisely what we need to explain this data. And it's not a black hole. It's not a black hole. It's an and people, I mean, this is not it's not easy. I mean, you need to, we are fighting successfully a battle because we are theoretical physicists and we can see the theory underlying, like we did for the black hole, like we did for the mass formula, which we are discussing with Professor Yao. We are theorists. The observational people have no understanding of the theory. They fit data. Therefore, for us, it's a necessity to have the core with dark matter. It's not an option. It's not an addition. If you pay for the flat rotation curve here, you need to have this. And this is what comes out. Therefore, it's not a black hole, it's just a system of self-gravitating fermions with no electric charge. Now, the people who do the experiment don't see that theory. I mean, the theory is difficult. It's not, for us, it's easy, because we have been working for 40, 50 years on this from the beginning. But for them, it's not easy. Therefore, today we were reading, maybe you tell a few feeling today with Orge, reading their paper. I said, oh yes, let us assume that it's a drag and interacting. Yes, but you have to explain the theory. You have to put in a set. I asked him to tell something on this, the feeling of today. The feeling of today, because it's only a few hours out.
The data you show, yes, is very reasonable. In 1 week, I saw the paper last week in the archive. Yes, this explained as the drag and the friction force between, but with baryonic matter, that they are assumed that there is accretion disk around a black hole, and they try to compute that. We computed already last year. We published our paper on the drag, on the friction force between dark matter particles and baryonic matter from our profile. Then I made an estimate of that, and then it cannot be like that, like they did. It cannot be such kind of drag force.
But because we have a theory.
and then came the additional point. This because we have a distribution, so an extended object is not a black hole, so as the system goes inside, so it is feeling the distribution of dark matter, and so a different gravitational field, different from the just simple 1 over r of a potential of a point light. And so this causes a different deviation from the Keplerian motion that they are observing. And the first estimate that we just made about that is that you have the right difference in gravitational potential to explain the deviation.
Tell what you, I mean, we are living this in real time. Tell what you told me walking in this Yacht Institute. It's good that we are on tape because this will be recorded forever. As we walked in, he said, not only, now you repeat it, because not only we can solve with 50 kV, we can solve, but we cannot solve with 20 kV, and we cannot solve for 70 kV. How much is your estimate? What is, please turn, you have to be on record. You have to be on record.
Okay, the issue is that it's for different particle masses, you didn't show you, but you didn't show them the different profiles.
You will tell tomorrow and so forth.
I can show the profile of the dark matter distribution depends on the particle mass you choose. And so the difference, how the deviation from just a Keplerian potential will change, depends on the particle mass. So you can compute in this fraction of distance that this object is moving, Okay, you can compute how this will deviate from the Keplerian motion. So you can, if the particle mass is lower than 50 keV, the effect would be too big, as the one observed. If the particle mass is bigger than 50 keV, the effect will disappear. This is the prediction we have right now.
It's bridged. We are getting there. Yes?
I try to understand his questions.
Which question?
His question is, does this dark matter carry dominant angular momentum as he carry the mass? Is your question?
Yeah.
It's spin. It's spin. It's spin 1/2.
Yeah.
Yes. It's if
Also, dark matter not only carry dominant mass, but also dominant angular momentum.
it's a spin 1/2 fermions, like the proton, like the neutron. It's spin 1/2. It's a fermion. Wang Yu, can you tell? We are still expecting the arrival from Iran of our closest collaborator, and Wang Yu will tell how we identify here the 15th of August the supernova, but he has been able to write the paper, and we never received. I usually, every paper is a fight, because the ideas are completely new, and so it's a tragedy, but we are used to that. Then after 1 year they agree and excuse and go on. But this is the first paper that we receive with all the congratulations. Tell what he said, the referee. And with all the happiness, he said, but this is the first.
Actually, the referee has any problem with the paper. He thinks that we did the first prediction.
And he said something more. He went through the literature. He said, "Oh, but you have done other predictions,
Yes.
and the other predictions succeed. But there are two which did not succeed. Can you tell us why they did not succeed?" Therefore, this referee really went through all the field, and of course we can explain easily because these objects were too far. And the supernova, you can see supernova only at redshift close. And if you go at z equal 1, it becomes problematic. And therefore, what happens is that the experimentalists, since was at z equal 1, quite far, they did not choose to risk the big telescope to look so far. And they used the big telescope VLT for the other source which we predicted. Therefore, the second source, fortunately, we had another one successful, and we will explain all this in the referee report. But later on today, there will be arriving the fourth person from Iran, who is from ICRANet in Pescara, but he's an Iranian, and then in order to get the visa to come to China, it was easier for him to fly from Rome to Iran and get the visa from Iran to China. And then he went from Iran to the beautiful place in the mountain in Urumqi, and then from Urumqi is arriving here. But still, it's exciting for him to see Urumqi. But anyway, he's reaching tonight, and there we have a great, great discovery to finish a paper with Shesheng. Tell a few seconds what we are looking, plus and minus.
No?
Yes, quickly. No, don't make a lecture. Just the topic. Just the topic.
We are trying to see another aspect of the black hole physics, which is how the electromagnetic field structure around the black hole, due to its rotation, due to its presence of the magnetic field, and how this electromagnetic potential is built, and one is electromagnetic field potential is built. You can do many work. For example, accelerating charged particles, or even vacuum if field is strong enough to produce a very high dense E plus E minus electron boson pair, and it's so dense, so energetic, they will the end release as a high energetic photon. And this counting for
the JEV radiation.
And high energy cosmic ray.
And high energy cosmic ray. No, namely, we can explain in principle now, finally, this object. We can explain how these jets are formed with JEV and ultra-high cosmic ray. Therefore, we are closing the loop to understand the birth of ultra-high energy cosmic rays. And all of four will be here during this week to work as hard as possible to complete the work.
Okay.
Thank you.
I have questions which relate to your presentation in NG15.
Yeah.
Does your proof of the Boissy
Yeah.
pulsate local mass
Yeah.
something to what's this angular momentum business enter to your this proof, which is positive energy?
The angular momentum is irrelevant to being positive, but on the other hand, there's a relation between angular momentum and mass. So we, at least in some important cases, we can prove that mass is always less than the angular momentum is less than the mass.
Yeah,
This is not trivial because it's true even locally. And of course, for K metric, which is a black hole, we know how to calculate it. We know the angular momentum is less than the mass, unless there's some bad singularity, which we don't allow. But this for general space-time, not just for stationary space-time. So for space-time, which is very general, we can do that. So most of the people in astronomy, I guess, assume that black hole is just a K metric. But here we're talking very general.
But here you see the nice picture Remo presents this spiral structure, which means the angular momentum is carried out away a bit from the center.
Right.
This is what the C.C. Lin discovered.
Right.
Okay, so then I start to think how to relate to your local. Your local, of course I haven't, your local of this quasi-local.
Right.
So which certainly contains gravitation, attractive negative energy, and then also difference.
Right.
So how then I start to think how this spiral something to do with your local positive.
Well, I need to do some calculation in this situation. It's not so easy. Our definition is general definition. I prove that in general there are some properties.
Yeah.
But in this special case, I need to calculate before I can start. Okay, other questions? Okay, so tomorrow there will be. Oh yeah. Forget. So in general, we have a presentation of the Lin lecture to you. So
thank
this
you.
will be taking a picture. Yeah.
Good.
Okay, good. So now you can put it up.
Thank you.
In your office.
Yes.
Good.
Good.
Thank you. So tomorrow at 3:20, I guess 3:20 there will be
Same room here.
same room by George. Tomorrow. Yeah. Good.
So more new discovery.
More
Yes.
to discuss.